Welcome to today's session. In this video, we'll delve into LeetCode problem number 1034, coloring a border. This problem challenges us to manipulate a grid by changing the border of a connected component. We'll explore various approaches, analyze their complexities, and discuss when and how to use them effectively. Let's get started. In this problem, you are given a grid, which is a 2D matrix where each cell is assigned an integer value. This value can be 0, representing white, or any number between 1 and 50, representing different colors. Along with the grid, you are provided with three additional inputs: row, col, and color. The row and col values specify the coordinates of a starting cell in the grid, and the color represents a new color that we need to apply. The task involves identifying the border of the connected component that includes the starting cell. A connected component is formed by all the cells with the same color as the starting cell, and these cells must be reachable via up, down, left, or right movements. The border of this component includes cells that are either on the edge of the grid or are adjacent to cells outside the connected component. Once the border is identified, we need to change the color of these border cells to the new color and return the updated grid. The output of this problem is a 2D integer array, which represents the modified grid after updating the border cells. Let's consider an example. Suppose the input grid is a 2x2 matrix, where the top left and top right cells have the value 1, and the bottom right cell has the value 2. The starting cell is at 0, 0, which is in the top left corner, and the new color is 3. The output grid will have the top left, top right, and bottom left cells changed to 3, while the bottom right cell remains 2. This is because the connected component includes the cells with the value 1 that are reachable from 0, 0. The border cells of this component are those that touch the grid boundary or are adjacent to a cell with a different color, which in this case happens to be all the cells in the connected component. To explain the previous example further, the starting cell, 0, 0, is part of a connected component where all cells have the color 1. This component includes 0, 0, 0, 1, and 1, 0. The border cells are the same as the connected component in this case because all these cells are either on the edge of the grid or adjacent to the cell, 1, 1, which has a different color. By changing the border cells to the new color 3, we get the output grid. Now, consider another example. Here, the grid is slightly larger, and the starting cell, 0, 1, belongs to a connected component with the color 2. The new color is 3. The result is that the border cells of this component, which include 0, 1, 0, 2, and 1, 2, are updated to the new color, while the rest of the grid remains unchanged. In the second example, the connected component includes the cells 0, 1, 0, 2, and 1, 2, all of which have the same color 2. The border cells of this component are exactly the same as the connected component because every cell in it is either at the grid boundary or adjacent to a cell with a different color. When we change these border cells to the new color, 3, the output grid reflects this update. Now, let's look at one more example. In this case, the grid is a 3x3 matrix where all cells initially have the same color, 1. The starting cell is 1, 1, and the new color is 2. Here, the connected component is the entire grid because all the cells are connected and share the same color. Since the connected component spans the entire grid in this example, the border includes all the cells along the outer edge of the grid. These border cells are updated to the new color, 2, while the inner cells retain their original color. The final output grid shows this change, with the outermost cells updated to 2 while the middle cell remains 1. This example illustrates how the border is determined when the connected component includes the entire grid. It highlights the importance of identifying which cells are at the boundary of the grid or adjacent to different colors. Finally, let's review the constraints and edge cases for this problem. The dimensions of the grid, m and n, can range from 1 to 50, and the color values in the grid are between 0 and 50. The starting cell's coordinates, row and col, are guaranteed to be within valid bounds, and the new color can be any value between 1 and 1000. Some edge cases to consider include when the entire grid forms a single connected component, making all the outer cells part of the border. Another scenario occurs when the connected component is completely surrounded by cells of the same color, resulting in no border cells. Additionally, if the new color matches the original color of the component, the grid remains visually unchanged. Finally, small grids, like 1 by 1 or 2 by 2, may have their entire grid as the border. These conditions ensure the problem is well defined and that the solution handles all possible scenarios appropriately. To solve this problem, one of the initial approaches we could consider is a brute force method that uses a flood fill algorithm. The intuition behind this is straightforward. We traverse all the cells connected to the starting point, grid, row, col, which share the same initial color. As we traverse, we identify which of these cells lie on the border of the connected component. A border cell can be defined as one that is adjacent to a cell of a different color or is located on the edge of the grid. Once identified, we recolor all the border cells with the new color. While this approach is simple to conceptualize, it has some drawbacks. First, it processes all connected cells, even the internal ones that don't need to be recolored, leading to inefficiency. Additionally, it requires extra steps to distinguish between border and non-border cells. This can result in a time complexity of O(m*(n), where m and n are the grid dimensions, making it less ideal for larger grids. Now, to address the inefficiencies of the brute force approach, we can use an optimized method based on depth-first search, or DFS, with border detection. Here, instead of processing the entire connected component, we focus specifically on identifying and recoloring only the border cells. As we perform the DFS starting from grid, row, col, we check each visited cell's neighbors. If any neighbor is out of bounds or has a different color, the current cell is classified as a border cell. By maintaining a set of visited cells, we ensure that we don't revisit cells unnecessarily. Once the traversal is complete, we recolor only the border cells. This approach is more efficient because it avoids unnecessary work on internal cells and has a lower memory footprint compared to brute force. Additionally, we could use a breadth-first search, or BFS, as an alternative to DFS. With BFS, we explore connected cells layer by layer using a queue, but the process for identifying and recoloring border cells remains similar. While BFS is a valid alternative, it comes with some trade-offs. Specifically, BFS typically has higher memory overhead because it relies on a queue to manage the traversal. On the other hand, DFS is more natural for recursive grid traversal and is generally preferred for its simplicity in this context. With that in mind, the chosen strategy for this problem is the optimized DFS approach with border detection. This method efficiently handles the task of traversing the grid while minimizing memory usage. Additionally, it recolors only the necessary border cells by identifying them during the traversal itself. A key observation here is that border detection can be seamlessly integrated into the DFS process by simply checking the neighbors of each cell. This insight eliminates the need for a separate step to identify borders and ensures a clear and efficient algorithm. By marking cells as visited during traversal, we also avoid revisiting cells and maintain a clear separation between different connected components. Finally, we should consider the trade-offs of this approach. While BFS could be used, DFS is preferred due to its simplicity and lower memory usage. In contrast, brute force methods were rejected because they involve unnecessary processing of internal cells and are less efficient overall. From a complexity perspective, the time complexity of this DFS-based solution is O(m*(n) in the worst case, as all connected cells may need to be visited. The space complexity is also O(m*(n), because we may need to store all visited cells in the worst case. Overall, this approach achieves a balance between efficiency, simplicity, and clarity, making it the optimal choice for solving the problem of coloring a border. To solve this problem, we begin by understanding the concept of border recoloring within a 2D grid. The task is to change the color of a connected component in the grid, starting from a given cell, but with a twist: only the border cells of the component should be recolored. A border cell is defined as one that either touches a cell of a different color or lies on the edge of the grid itself. Now, a simple brute force approach to this problem involves using a flood fill technique. First, we initialize our variables. We extract the original underscore color from the starting cell, which helps us identify all connected cells that need processing. If the original underscore color is the same as the new underscore color, no changes are necessary, so we can skip further processing. To handle traversal of the grid, we define a directions array to move up, down, left, and right, which ensures we cover all possible neighbors during the flood fill operation. Next, we perform a flood fill to identify all cells belonging to the same connected component as the starting cell. Using either DFS or BFS, we traverse the grid and collect all cells that share the same original _ color. To avoid revisiting cells, we maintain a visited matrix. During the traversal, we explore each valid neighbor, ensuring it is within the grid boundaries, not yet visited, and matches the original _ color. These connected cells are stored in a component list for later use. Once we have the entire connected component, the next step is to identify which of these cells are border cells. For each cell in the component, we check its neighbors in all 4 directions. If any neighbor is either out of bounds or has a different color, that cell is marked as a border cell and added to a borders list. Finally, we recolor these border cells by iterating over the borders list and setting their color to the new _ color. The modified grid is then returned as the result. There are a few key insights to keep in mind for this algorithm. First, the flood fill algorithm is fundamental to identifying all connected cells. While both BFS and DFS can achieve this, BFS is often preferred for its iterative nature, especially when recursion depth is a concern. Second, the real challenge lies in identifying border cells efficiently, which requires checking the neighbors of each cell during traversal. To optimize this process, instead of storing all connected cells in a component list and processing them separately, we can directly check for border conditions during the flood fill itself, reducing space usage. Additionally, several edge cases must be considered, such as when the grid consists of a single cell, the starting cell is already a border cell, all cells in the grid share the same color, or when the new _ color matches the original _ color, meaning no changes are needed. For this algorithm, we rely on several data structures to ensure efficient implementation. The grid itself, represented as a 2D list, serves as the main input. A visited matrix, also a 2D list, helps track which cells have already been processed, avoiding redundant computations. Depending on the traversal method chosen, we use either a queue for BFS or a stack for DFS to systematically explore connected cells. While a component list can be utilized to temporarily store all connected cells, we can optimize by skipping this step and directly checking for border conditions during traversal. Finally, a borders list is essential for storing identified border cells that need recoloring. Analyzing the complexity, the time complexity is O and *m, as each cell is visited at most once during the flood fill and border identification. The space complexity is also O and *m, accounting for the visited matrix and optional storage for connected components, ensuring the algorithm remains efficient even for large grids. Here, we start by importing DEEC from the collections module and defining a solution class with the method colorBorder. The method takes in the grid, the starting cell's row and column indices, and the new color. We first determine the dimensions of the grid, M and N, and store the original color of the starting cell. To keep track of visited cells, we use a set, visited, and maintain a list, border _ cells, to store the coordinates of all cells that form the border of the connected region. Next, there's a helper function is _ border, which checks if a cell is on the border of the grid or if it is adjacent to a cell of a different color. It does so by iterating over the 4 possible directions right, down, left, and up and checking if the neighboring cell either falls out of bounds or does not match the original color. If either condition is true, the cell is part of the border. Then, we define a depth-first search function DFS that explores all connected cells of the same color. It marks the current cell as visited, checks if it's a border cell, and adds it to border _ cells if necessary. The function recursively visits all valid adjacent cells that match the original color and haven't been visited yet. Once the depth-first search is complete, the DFS function will have identified all the border cells of the connected region. For each of these border cells stored in border _ cells, we update the grid by changing the cell's color to the new color provided as input. Finally, the method returns the updated grid, completing the task of coloring the border of the connected region while leaving the interior cells unchanged. This implementation ensures that we only traverse the necessary cells and efficiently modify the grid as required. Here, we begin implementing the solution in Java. First, we define the colorBorder method, which takes the grid, the starting cell coordinates, and the target color as input. We start by determining the dimensions of the grid and storing the original color of the starting cell. A visited array is initialized to track which cells have been processed, and a list called border cells is created to store the coordinates of cells that belong to the border of the connected component. Next, we define the isBorder helper method. This method checks if a given cell lies on the border of the grid or is adjacent to a cell with a different color. If the cell is on the edge of the grid, it's immediately marked as a border. Otherwise, we loop through each possible direction right, down, left, and up and check the color of the neighboring cells. If any neighbor has a different color than the original, the cell is part of the border. This helper function ensures that we can accurately identify border cells as we traverse the grid. To explore the connected component, we define the DFS method. This recursive function marks the current cell as visited and checks if it's a border cell using the isBorder method. If it is, we add its coordinates to the border cells list. Then, we iterate through all 4 possible directions right, down, left, and up and calculate the coordinates of the neighboring cells. For each neighbor, we ensure it lies within the grid boundaries, hasn't been visited yet, and has the same color as the original cell before calling DFS on it. Once the depth-first search is complete, all border cells of the connected component will be identified. Finally, we loop through the border cells list and update the color of each border cell to the target color. The modified grid is then returned as the result. This approach ensures that only the border cells of the connected component are recolored, with all other cells remaining unchanged. In this basic example, we begin by examining the input grid, which is a 2x2 matrix. The starting cell is at position 0, 0, with a color value of 1, and we are tasked with changing the border cells of this connected component to the new color, 3. First, we initialize some variables, the grid dimensions, the original color of the starting cell, and 2 empty sets, one to track visited cells and the other to store border cells. Using depth-first search, we start at 0, 0. This cell is immediately marked as visited, and since it lies on the edge of the grid, it is identified as a border cell and added to the border_cells list. We then explore its neighbors, starting with 0, 1, a valid cell of the same original color that hasn't been visited yet, prompting a recursive DFS call. Now at 0, 1, the cell is added to the visited set. Since it is on the edge of the grid, it is identified as a border cell and added to border_cells. Next, we examine its neighbors. The cell, 1, 1, has a different color, so it is skipped. However, 1, 0, is a valid neighbor with the same color and hasn't been visited yet, so we proceed with a DFS call to 1, 0. At 1, 0, the process repeats, the cell is marked as visited, recognized as a border cell due to its position on the grid's edge, and added to border_cells. Since all of its neighbors are either visited or of a different color, the DFS concludes. At this point, the border cells have been identified as 0, 0, 0, 1, and 1, 0. Finally, we update the border cells in the grid to the new color, resulting in the output grid 3, 3, 3, 2. In this larger example, the grid is a 3x3 matrix, and the starting cell at 1, 1 has an original color of 2. Our task remains the same, to recolor the border of its connected component. After initializing the grid dimensions, original color, visited set, and border_cells list, we begin DFS from 1, 1. The cell is added to visited, and we check whether it qualifies as a border cell. Since one of its neighbors, 1, 0, has a different color, 1, 1, is deemed a border cell and added to border_cells. At this point, all of its neighbors are either visited or of a different color, so there are no further recursive calls. With the border cells identified, we update the grid by applying the new color to the border cells, resulting in the output grid 1, 1, 1, 1, 3, 1, 1, 1, 1. Next, we analyze a more complex grid with a shape that includes multiple connected border cells. The grid is 4 times 4, and the starting cell at 1, 1 has an original color of 2. As usual, we initialize the necessary variables and start DFS from 1, 1. This cell is added to the visited set, and upon examining its neighbors, we find that 0, 1 has a different color. Thus, 1, 1 is identified as a border cell and added to border_cells. From here, DFS proceeds to 1, 2, another cell of the same original color. At 1, 2, the cell is marked as visited and is also found to be a border cell due to its neighbor, 0, 2, having a different color. The DFS then continues to 2, 2, progressing further along the connected component. At 2, 2, the cell is marked as visited and checked for border status. A neighbor, 2, 3, has a different color, so 2, 2, is classified as a border cell and added to border underscore cells. From here, DFS moves to 2, 1. At this cell, we repeat the process, it is added to visited, and since one of its neighbors, 3, 1, has a different color, 2, 1, is also identified as a border cell. With the DFS complete and all border cells identified, we proceed to update their colors in the grid. The final grid, after recoloring the identified border cells to 3, is 1, 1, 1, 1, 1, 3, 3, 1, 1, 3, 1, 1, 1, 1, 1, 1. The time complexity of this solution is primarily determined by the depth-first search traversal and the associated operations performed during it. First, let's consider the traversal itself. The DFS function systematically visits each cell within the connected component of the grid that shares the same color as the starting cell. If we denote the size of this connected component as k, then each cell within this region is visited exactly once. For each cell, the function explores its 4 neighbors, checking if they are within bounds, share the same color, or need to be marked as visited. These per-neighbor operations each take constant time, and since every cell has exactly 4 neighbors, the work done per cell is constant. As a result, the traversal of all k cells incurs a time complexity of O(k). Additionally, there's the border check, where each visited cell is evaluated to determine if it qualifies as a border cell. This also involves iterating over its 4 neighbors and performing constant time checks, contributing another O(k) to the overall complexity. Together, these steps make the traversal and border check processes efficient, scaling linearly with the size of the connected component. Now, focusing on coloring the border cells, the algorithm processes each cell in the list of border cells and applies the specified new color. Let's denote the number of border cells as B. Since the border cells are a subset of the connected component, B is always less than or equal to K. Iterating over this list and modifying the color of each border cell takes O(B) time, which is at most O(k). Combining all these operations, the dominant term in the time complexity is the DFS traversal, which is O(k). In the worst-case scenario, where the entire grid forms a single connected component, the value of k becomes m*n, where m and n are the dimensions of the grid. Therefore, the worst-case time complexity of this solution is O(m*n). Next, let's analyze the space complexity of the solution, which depends on the additional memory used for the recursion stack, the visited set, and the border cells list. First, the recursion stack. Since the DFS is implemented recursively, the maximum depth of the recursion corresponds to the size of the connected component, which is k. In the worst case, where the entire grid is a single connected component, the recursion depth can reach O(m*n). Second, the visited set stores all the cells within the connected component, so its size is also O(k), which again becomes O(m*n) in the worst case. Third, the border cells list contains only the border cells of the connected component. Although smaller in size, its maximum length is still O(k), and becomes O(m*n) in the worst case. These 3 components together determine the overall space complexity. The dominant factor in the space complexity is the recursion stack, which means the overall space complexity is O(m*n) in the worst case. Let's compare this optimized approach to a naive solution. A naive approach would involve iterating over every cell in the grid, checking its color, and determining whether it is part of the border. This would require a full traversal of the grid, resulting in a time complexity of O(m*n), even for smaller connected components, and additional checks for every cell would further increase inefficiencies. In contrast, the optimized approach restricts the DFS to the connected component of the starting cell, avoiding redundant checks and ensuring the algorithm processes only relevant cells. This makes the solution more efficient, particularly when the connected component is much smaller than the grid. By leveraging properties of connected components and recursive traversal, the solution achieves the same worst-case complexity as the naive approach but performs significantly better in average cases. Finally, let's consider the best, average, and worst-case scenarios for this solution. In the best case, the connected component is very small, such as a single cell. Here, the time and space complexity are O(1), as only one cell is processed. In the average case, the connected component encompasses a fraction of the grid, say k cells. The time and space complexities in this case are O(k), which is smaller than the total grid size m*n. In the worst case, the connected component spans the entire grid, resulting in time and space complexities of O(m*n). This solution is designed to handle all cases efficiently by limiting operations to the connected component, ensuring both scalability and optimal performance regardless of the grid size or the structure of the connected component. When solving problems like coloring a border, there are some common mistakes to watch out for. First, when using recursive depth-first search, it's easy to forget to reset the visited states for cells. This can lead to infinite recursion or revisiting the same cells repeatedly, which will result in a time limit exceeded error. To prevent this, you can either use a visited set to track process cells or modify the grid in place to mark them as visited. Another frequent mistake is misunderstanding problem constraints. For example, ignoring the boundaries of the grid can lead to out-of-bound errors. Always validate your indices to ensure they're within the grid's limits. Lastly, brute forcing the solution, such as recoloring the entire grid multiple times, can be highly inefficient, especially for large grids. Instead, consider using techniques like memoization or iterative approaches to optimize performance and avoid redundant computations. Off-by-one errors and loops are another source of mistakes in grid problems. These occur when loop bounds are not adjusted correctly, which can cause you to miss edge cases, particularly around the grid's boundaries. Carefully verifying loop ranges and testing edge cases, such as single row or single column grids, can help avoid this issue. Speaking of edge cases, it's also important to explicitly consider scenarios like grids where all cells are the same color, grids with only one cell, or cases where there are no valid moves. Failing to account for these can leave your solution incomplete. To address this, make sure to write test cases that cover all these potential edge scenarios to ensure your code handles them correctly. When preparing for interviews, there are a few insights to keep in mind. Be ready to explain the trade-offs between using depth-first search and breadth-first search. While DFS is often simpler to implement recursively, BFS might be more intuitive for problems involving shortest paths. Optimization is another key discussion point. Once you've implemented a basic solution, explain how you can improve it. For instance, you might optimize for memory by modifying the grid in place instead of using a visited array, or improve time performance by avoiding unnecessary grid scans. Also, make sure you can articulate how your solution handles edge cases, such as disconnected regions or grids where all cells are already processed. If the constraints involve large grids, discuss how your solution adapts, such as by avoiding excessive recursion depth. Finally, highlight your testing strategy. Start with small grids for debugging and scale to larger inputs to validate performance. To deepen your understanding, you can explore related problems like LeetCode 200, number of islands, or LeetCode 733, flood fill. These problems share similar concepts, such as traversing connected components in a grid. Other examples include LeetCode 695, max area of island, and LeetCode 130, surrounded regions. Considering alternative approaches is also valuable. For instance, recursive depth-first search is often a natural fit for exploring connected components because of its simplicity. However, it can lead to stack overflow on large grids. Iterative breadth-first search avoids this issue by using a queue, making it a better choice for problems that require level-order traversal. That said, BFS typically requires additional data structures and may be less straightforward to implement than DFS, depending on the problem. Another approach worth considering is the union find, or disjoint set, method. This is particularly efficient for problems that require frequent connectivity queries between components. However, union find can be more complex to implement and may feel less intuitive for flood fill style problems. Finally, in-place grid modification can save memory by eliminating the need for additional data structures like a visited set. This can be especially useful when memory is a constraint. However, modifying the input grid directly might not always be acceptable in an interview setting, as it alters the original data. It's important to weigh these trade-offs and choose the approach that best fits the problem constraints and requirements. Great job! We explored the coloring a border problem, summarized the key concepts, and discussed the importance of flood fill algorithms. Don't forget to practice similar problems to strengthen your understanding. Thanks for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!